Good evening, ladies and gentlemen. It gives me great pleasure to welcome you here tonight to Engineers Ireland on behalf of the Structures and Construction Division. Just a couple of housekeeping items to run by. First of all, can you please note the two fire exits, the doors you came through, and those down here to the right-hand side. Secondly, just as a matter of courtesy to our speaker, could you please kindly turn off your mobile phones? So I think we have a very interesting lecture here tonight. The title is Bridges, Evaluating for Scour Using Traditional and Modern Techniques. Our speaker is Brian Devlin, Managing Director of Collins Engineers. Flooding is becoming more and more prevalent in Ireland, and the effects of fast-flowing water on infrastructure is becoming more important to engineers. Scour is the key reason for failure and partial collapse of bridges around the world. This presentation will discuss the types of scour that exist and contributing factors. Brian will also be discussing alternative technology used to ensure the safety of bridges. I would now like to hand you over to our speaker for tonight.
Okay, thanks, Kerry. As Kerry said, scour is probably the most common cause of bridge failure throughout the world, and at this time of year generally is a talked about topic, and particularly in Ireland now that you've got heavy rainfall becoming more and more prevalent, faster runoff, that type of thing. Consequently, all bridges should be evaluated for scour or assessed for vulnerability due to floods. Okay, so what I'm going to discuss tonight basically is the first half of the talk is basically on the various types of scour that can exist and describe a bit in detail on that. Then I'll go on to talk, really concentrate more on the modern techniques associated now with assessing bridges for scour, using 2D imaging, acoustic imaging, and the 3D mechanical scanning multi-beam. Good tool that the engineer divers would use, particularly in fast flow conditions. Okay, so this is a picture of an exposed pile that our engineer divers came across on a structure. No issues from above water, no issues with the structure, but it just shows the importance of underwater inspections for bridge owners. There's a definition of scour, so effectively it's the action of flowing water eroding the channel bottom. The lighter the material or the faster the velocity, then the greater the scour. So where you've got fines, they will be easily eroded, and if you've got heavier material or more cohesive material, it tends to be more scour resistant. Okay, the first type of scour is aggradation and degradation. So basically degradation is the long-term lowering of the channel bottom as a result of natural or man-made causes. Usually occurs over the long stretches of the waterway and across the full width of the channel. Aggradation is basically the opposite of that, is the long-term build-up of channel bottom material. So here's an image. Thankfully, we haven't come across in our studies anything in Ireland. But this is an image of an extreme situation where you've got degradation of the channel bottom across. You can see it there across the full width of the channel. And normally, if there's bridges along the waterway in the same stretch, other bridges would be affected. And I think the cause of this one was due to dredging of the channel bottom nearby. General scour. General scour comes in two forms, basically contraction scour and the other form of general scour. Contraction scour is basically the where you've got a confine in the channel or a natural contraction in the channel, or as a result of a bridge where the velocity is increased because the cross-sectional area is decreased. So an example in this, you can see on the bottom cross-sectional area, basically where you have the velocity is increased in the contracted area, the channel bottom material will be eroded, leading to an increase in the cross-sectional area, and then you've got the resulting in the velocity decreasing until there's a point of equilibrium achieved. The upper cross-section results in, there's a bend really in the channel in the upper cross-section, and that shows the erosion taking place on the outer bend, where the velocity is greater. Consequently, you have to be careful in assessing a bridge, basically that your foundations, you looked at each situation, because obviously the centre or the left-hand side will not be as affected as the right-hand side on the outside of a bend. So that's why it's very important when you're doing inspections on site, you note where the bridge is in the straight part of a channel or at a bend. Ideally it should be, when they're constructing it, it should be at a straight part of the channel, or realign the channel during the bridge construction works if you're putting in a new structure. So there's an example of a contraction scour. Basically the flow is the product of velocity times the cross-sectional area. So where you've got approach embankments coming out to the structure, you obviously have a reduction in the cross-sectional area, resulting in an increased velocity, and consequently that increased chance of scour occurring. Another one here is the effect of your abutment types. So on your right hand side at the top there, you've got basically closed abutments. So you've got a reduced area, so consequently you'll have an increased velocity on a like-for-like basis compared to the left-hand side, and as a result of that, where you've got the closed abutments and an increased velocity, you've a greater risk of undermining, because the abutments are much closer to the main river channel. Whereas if the abutments are further set back, you've got the increased area, lower velocity, and reduces the risk of any undermining, because it's set further back from the main river channel. So that's also something to take into account during your inspections, to note that, or when you're designing or constructing new structures. Okay, other general scour is basically at bends in channels, or as a result of dredging, or effects on the channel itself. Here you've got general scour. If you look at the top slide, where you've got, I've touched on this earlier, but you've got on the outside of the bend a greater velocity, resulting in increased scour, but on the inside of the bend the velocity is much less, and you normally would have deposition of material in this area, and that can affect the balance of the two-span structure as well. So when a major flood comes through, you've got material building up on the left-hand side, so that also has a double whammy effect on the outside of the bend, where the water is forced to the other span, where you then get an increase in scour. The bottom slide, the bottom cross-sectional area there, is basically where you've got, again, material being eroded, resulting in more piles becoming exposed. And a good example of that was the River Hatchie Bridge in Tennessee in the late 60s, where it collapsed because more piles became exposed because of what is known as lateral erosion, or another form of general scour. And eventually the bridge collapsed, and I think there was a death of maybe 60 to 70 people. That was a good case study, because a number of inspections had been carried out throughout the years, and the channel bottom was being mapped, and the river was being mapped, but nobody was really joining the dots that actually lateral erosion was occurring. So everybody was taking a snapshot in time. The structure was stable, but nobody was mapping it that there's going to be lateral erosion occurring, resulting in piles that originally would have been on approach embankments, then becoming more exposed, where they weren't meant to be basically exposed, and resulted in the collapse of the structure. From there, the Federal Highway Administration in the US basically beefed up their inspection regime and their desk study regime in accordance with what's known as the standard HAC 18, which a lot of the local standards are mirrored on. So here's an example of a local bridge where we inspected it for Irish rail. So if you look at basically at the right hand side, the channel bottom is eroded to the right. If you can see where the pier is, you can see like a meandering effect of the channel, where at one stage it was probably coming straight through the middle of the bridge, but because of the soft material, if you look at the embankments there, it's basically a straight cut with a water line. but that's very soft material, so it's being eroded. So what happens in major flood situations is the wing wall on the right hand side is being attacked and being undermined, and material taken out from the rear of the wing wall. So in a situation like that, it's very important that the client will stabilise that wing wall, dig back and put in heavy rock armour to protect it from in a flood situation. Other forms of general scour is basically due to man-made events. So example of this is dredging. You can also get situations like where you install cofferdams in a river, or such things as sluice gates or dam gates, which basically a river is a natural cycle fill material of erosion and fill material along a channel. So if you introduce short-term man-made effects, that can create an imbalance in the channel, and can have an effect on your structure. That's something also to be taken account of. So I know the likes of Irish Rail now, if there's any developments upstream of the structure or downstream of the structure, they tend to be made aware of it and insist on a hydraulic study being carried out on the development to see what effect it will have on the river and particularly on their structure, and something that all engineers should take account of, and particularly planners as well. Local scour is probably the most common form of scour that can occur, and it basically occurs around piers, abutments and embankments, and is due to like a pile up of water or due to a local obstruction in the channel. So we've got basically an example here of a pier, and you can see the pile up of water occurring on the back of the pier. That creates what is known as a horseshoe vortex, and when the scour depth increases, the horseshoe vortex will effectively decrease till you reach a point of equilibrium and no more scour will take place. You also get the vertical wake vortex around the downstream end of the pier, and you usually find then immediately further downstream of that you get a deposition of material, of the material that has been scarred from around the pier. So here depicts basically the flow. You can see the flow hitting the bridge pier on plan at the top, and that's the sort of effect that it has around the bridge pier itself in terms of the sort of circumference of influence. And then on the bottom here you've got an elevation. So basically what happens is you've got erosion or scarring at the upstream end and along the upstream end of the pier, and deposition of material along the downstream end. I should show you, I think the next image will show you a good example of that. So this is basically 2D acoustic imaging, which we'll talk about later, but I put it in here because you can see on the right hand side that's basically the upstream end of the structure. So the flow is coming from your right to left, and you've got erosion around the upstream end of the structure and the deposition of material then further on down along the pier. And you can see the bridge footing itself there at the top of the footing. So local scour depth factors, basically the greater the velocity, the greater the scour depth. Fines are, as I said, are eroded much more quickly. Consequently, that's why basically if you put in rock armour, it usually can resist scarring effects, and is a common recommendation to stabilise any additional scarring occurring around a structure. But it's very important that if you are designing rock armour that you don't overfill a situation, because that can effectively increase the width of the pier if you overfill with rock armour around a pier, because it basically can add to the obstruction. So it's very important to create a balance and try to make it natural as much as possible with the channel bottom, or if you're infilling a scar hole, to don't come higher than the channel bottom itself, or it'll become an obstruction in itself and just create greater scar. Because depth of flow as well, so the greater the depth of flow, the greater the velocity, and the greater the scar depth. So effectively the scar depth is increased by a factor of 2 relative to the depth of flow itself. The width of pier obviously is very important in terms of the which is common to the angle of attack. So basically those 3 points in the middle, the width of the pier, the length of the pier, skewed to the flow, and the angle of attack are all interrelated. And the angle of attack is very important, and you note that during an inspection, because it can change during a flood situation as well. The angle can change, but it's very important that's noted during an inspection of the angle of attack, because that feeds into the calculations if you're doing a desktop study on the structure, and it's becoming at a greater risk. The length of the pier skewed to the flow effectively. So if you've got where the pier length is increased, the scar can increase by as much as 30 to 60%, where the length of the pier is doubled effectively. Debris, the presence of ice and debris, particularly debris in this country, effectively increases the width of the pier, and you have scar occurring around the debris, and I'll show you an image of that. The shape of the pier as well, itself as well, so if you've got a square face or round face, or what is known as well in terms of cutwaters, can have the effect on local scar. So you try to get a pier that deflects the flow around it as opposed to a flat face where the flow is hitting it straight on. So basically if you've got like a tree lodged in the upstream end of a pier, which is not uncommon during flood situations, what will happen is that diverts the flow around, and you'll end up getting scarring, because effectively you're increasing the width of the pier, or the obstruction to the water as it comes along, and then effectively when the tree is removed, you usually get infilling occurring, and if the inspectors aren't out there at the time, the infilling hides the effect of the scar that happened. So it's very important that inspections are carried out as close as possible to any major flooding events. So here's a typical image that we had come across when we go to site to carry out underwater inspections. This debris at the upstream face, very common, particularly during flood situations where you've got basically small debris builds up, and then eventually that just gathers and gathers more material as it comes downstream. It's very important that that's removed reasonably quickly, or when the next flood comes along. That's basically your effective width of the pier there, and you can see that's actually a cutwater pier, but it's not working when you've got a situation like that. We normally advise bridge owners to remove that. In some situations there's a debate as to who's responsible for moving the debris, but my opinion would be that if it's your structure, you should go in and remove it, because you're the primary owner, and it's very important from a public safety point of view. So don't basically hang about and argue with others in terms of removal of debris. The fact of the pier shape, so where you've got a sharp nose or a cutwater, it's normally has a 10% less effect compared to a rounded nose pier, whereas the square face can have a 10% increase in scarring relative to the round nose. So again, something to take account of when you're designing structures or assessing structures on site for scar. So basically, summing up then in terms of scarring, total scarring occurs during maximum flow, and there's a combination of the local scarring effect from the obstruction itself, the contraction scour, which is basically across the full width of the channel, and can be as a result of the bridge itself or approach embankments, or a natural reduction in the channel itself, and also long-term effects. And the combination of this is normally assessed as well in terms of a desktop study, if perhaps in accordance with BD 9712 from the DMRB, where you'd look at these effects, and basically if your stream bed is a certain point, that the cumulative effects of the scar should be a certain distance or factor above the underside of your footing, just to ensure stability of your structure. So that's it really in simplistic terms. So when you're carrying out inspections or assessing structures, you're trying to really determine Scour-Critical Bridges, and this is usually determined from an on-site inspection where your foundations would be determined to be unstable during the actual scour event or immediately following the scour event, or where it's potential to become unstable from a study which I've mentioned in terms of BD 9712, which is basically a two-stage process where you conduct your inspections on site and note all the effects, not only the bridge itself but also the river channel. Is the river channel stable? Is it vegetated? Ensuring that it's not heavily vegetated where it can become an obstruction to the waterway during a high flood situation. Also, is there things like embankments where if you've got steep embankments and you've got a heavy flooding occurring, it dissipates the flow. If you've got a floodplain, which is a much better situation to have, whereas if you've got heavy embankments, that can create the contraction scour effect because the flow is forced through the channel waterway. Other things to note as well then is, taking your soundings upstream and downstream of the channel. Is there already scour holes or natural holes in the channel? Is there a build-up of material over time? Then itself, in terms of the abutments, are they closed abutments, are they open? Is there any relief channels nearby? If the flow builds up, can it be relieved elsewhere? All those effects, as well as the gradient of the channel and the roughness of the channel, so that you can determine the Manning's coefficient. All that comes into the desktop study. So basically, as I mentioned there, you're basically recording the present condition of the structure and the channel bottom and the waterway itself, upstream and downstream of the structure. Very important to capture some images as well, upstream and downstream, and monitor it going forward. Identify conditions indicative of potential problems. If there's nearby waterway walls, retaining walls, are they being attacked as well? Because they can obviously are constructed to protect the bridge itself. So if those are being attacked, it's very important that they are stabilised to protect the main primary structure. So, when is it best to conduct scour inspections? Ideally during a major flood event, but as you can see from a typical image, that can prove very difficult and most instances unsafe from a health and safety point of view, to put divers in the water or even to put vessels and boats along with equipment to undertake soundings. After a major flood event, that's probably the next best time to in terms of capturing the information before what is known as infilling can occur. And the floods can dissipate, and normally you can get maybe divers in the water to conduct the inspection before full infilling can take place. And also, if a bridge owner has their bridge closed, it's very important to get in as quickly as possible, so that the bridge can be determined whether it's safe or unsafe. As part of a scheduled inspection, more and more bridge owners are conducting scheduled inspections, and they generally range from maybe 3 years to 6 years. I know Irish Rail and Network Rail in the UK would have a 3-year policy on structures, and then from there they'd be risk assessed. Could the scheduled inspections be lengthened periodically? But normally they go now for a 3-year inspection. Previous to the Malahide Bridge collapse, they were a 5-year or 6-year inspection, but they've beefed up their policies and their regimes following a full analysis of the procedures following the Malahide collapse. The only problem with conducting it as during a scheduled inspection is, it's normally you would conduct that during low flow, perhaps in the summertime, so you don't see things like the angle of attack from major flood situations. So it's very important to note, is there floodplains upstream and downstream embankments? Also, one fact too is where I mentioned about infilling, so trying to determine is there soft penetration of the channel bottom and around the structure. So our guys would normally inspect and determine the depth of penetration, as that can tell you a lot about the channel bottom in terms of its erodibility. So here's a photograph of a bridge over the River Suck in Ballinasloe during a major flood event in December 2009. people maybe recall when the town of Ballinasloe was heavily flooded, our engineer divers were called out to this structure, and where Irish Rail had a real genuine concern about it. When we went out, you couldn't actually recognise where the waterway was. You know, it's the bridge that basically showed you where the waterway was. There's a massive floodplain, heavy flooding there, and the concern about that structure at the time too was you can see the lower girder and how close it is to the water line, and obviously if there was any debris or major debris washed downstream and became lodged in that girder, then you could effectively end up having movement of the structure laterally. So it was a real concern for them. But obviously the main concern is the Galway line was closed down at that time due to flooding, but also because of the structures like this. Because of the fast flow in the river, it wasn't advisable or safe to be putting engineer divers in the water, never mind putting a boat in the water. So in a situation like this, thankfully there had been previous inspections carried out on this structure, so we were able to pull up the previous report, determine if there was like aprons on the channel bottom, if it had any problems in the past in terms of scarring, what was the profile of the channel bottom. So effectively what we did in a situation like that was we took soundings at the structure from above the structure itself, which the water depth to the channel bottom. We were able then to compare that with the previous reports and previous inspection notes to see if the channel bottom was moving. And in a situation like that as well, then we undertook 2D acoustic imaging, which profiled the channel bottom relative to the masonry walls, masonry piers, and you're able to see if there's any scarring occurring. And from that situation, then the bridge owner was able to make a determination as to whether to open up the structure or not. And thankfully, he was able to open it up within a few days. Whereas if you didn't have a situation like that, you'd have to probably wait till the floods recede and then put divers in the water. But you can imagine then the Dublin-Galway line closed down for a number of weeks, which probably wouldn't have went down well politically. So in terms of the diver inspections for Scour, divers do have a limited view in terms of what they can see, particularly where you've got poor visibility, and some instances zero visibility. It turns out to be a tactile inspection. It can be obviously hard for divers to estimate sizes in situations like that in terms of measurements. Again, you can have possible infilling of material, or the diver can find it hard to detect if there's scar having occurred in the recent past. And obviously during flood flows it can be difficult access in most situations because of flood flows. The currents are too fast for allowing the divers to get into the water because effectively they can't stand up. So basically scar can only be measured with certainty during high flood events, because that's when the major undermining or scarring is occurring, and just re-emphasising infilling occurs during periods of lower flows. So moving on in terms of the acoustic imaging of structures using our modern techniques. This is obviously humans. The human mind has a tendency for out of sight, out of mind, but bridge owners nowadays are becoming more and more acutely aware of the need to ensure the integrity of their structures underwater, as they in most cases support the structure above water. So this is what happens when you undertake the acoustic imaging, and a good example where you've got the channel bottom erosion exposing the footing. So in a situation like this, it's obviously of concern to the bridge owner, where you'd have to move in and do some rock armour repair works around the footing. Very useful technology, gives you an image and a baseline for future monitoring of the structure, and allows obviously the bridge owner to see the full structure, and gives them the full picture, whereas it can be difficult sometimes for divers to pick up that information. So what is sonar? Basically sonar is emits a a sound in the water column and measures the time taken for the sound to travel to the source, to the target, and then back to the source. So 2D sector scanning sonar is a sonar head remains stable while the transducer rotates, so it's effectively like shining a light on a surface, and casts a single beam around the image that you're trying to pick up. So what is sector scanning sonar? It's basically, how is it undertaken? It's basically undertaken from a boat with two guys, and it's lowered with a tripod onto the channel bottom, and as I say, it's like shining a light. So here an example of dock wall joints, masonry joints out in Egypt, where you can see heavy or severe opening of the joints, and that it's useful that it can be used by the divers as to where the divers should focus their attention when they're carrying out underwater inspections, and also it can be used for picking up major debris in the channel bottom before you put divers in the water, because obviously there's a risk of entanglement when divers are put in the water, so it's very important from a health and safety point of view. Sector scanning sonar, it can be used for, depending on how it's set up, it can be used to pick up a plan view on the channel or an elevation view of the structure. And if you look at the bottom image, it can pick up certainly the pile arrangement and more detail on the structure, and you can see those old wooden piles, some of them continuing to the channel bottom and some of them severed on an old decaying structure. It can also be used from an archaeological point of view, and this is something that we had captured when we were inspecting a quay wall in Dublin, an old vessel on the channel bottom that the owner wanted us to pick up, the sunken vessel, and you can see the profile of the channel bottom itself. And I know police forces, certainly in the UK and probably in Ireland now as well, would own a number of these devices that's used for detecting bodies and explosive devices underwater and that type of thing. Here's I think this is possibly the Liffey quay wall in Dublin, where you can see there's imaging carried out of large stretches of the wall and major voids picked up. That allows you then to focus the attention of the engineer divers to and inspect those areas rather than concentrating, or rather than inspecting long stretches of wall at huge expense. They can focus their attention where you've detected issues in the imaging, and then you can see the photographs at the bottom where it's verified that there are voids in the wall. So this is the image I showed you earlier. This is actually Charlemont Bridge in Portadown, Northern Ireland, where we had carried out underwater inspection for road service, and then they had commissioned us to undertake underwater acoustic imaging, so that they could use the information for coming up with a repair contract, and then also supplying this information to the contractor. Obviously it reduces the contractor as well in terms of pricing, so that he knows what he's dealing with, rather than notes from divers and that type of thing. On the right hand side, actually, though you can't see it in the image, but the divers verified that there was timber piles exposed and horizontal struts exposed from the old structure. Here's another example of 2D scanning of a sheet pile wall, and you can notice the texture of the channel bottom material in terms of riprap and finer material, and where you've got the scar hole there within the circle, the owner of the wall would want that infilled with rock armour and smoothed out. We were then brought in after the event, and you can see that the contractor effectively just dumped the armour as opposed to placing it and spreading it out. So effectively, what I mentioned earlier, that can create another obstruction and just result in further scarring out. So it has an effect as well in terms of monitoring for infrastructure owners that contractors are performing the works adequately and according to specifications. You can see actually where the scar hole was, if you can look at the photograph in the top centre, where there was a sinkhole in behind the wall, and that obviously led to the concern and why there was imaging undertaken in the first place. So basically, the advantages of the 2D sector scanning sonar is very easy to use and adaptable to imaging of vertical surfaces. Doesn't provide 3D data, but as I say, it has its uses, and very simple to use, and quickly you can provide the post-processing information reasonably quickly. Usually, if you're in the field one day, then the imaging can take approximately the same amount of time by an engineer. 3D mechanical scanning. This is basically what is known as a blue view. The image here is a blue view device, BV 5000 multi-beam sonar, worth of probably about 150,000 euros. So very expensive equipment. So not cheap to rent out either, but again, simple to deploy from a vessel, 2 guys in the vessel, and deploy it on the tripod to the channel bottom, and can be used for imaging, and I'll show you good examples coming forward. So basically it's a multi-beam 3D image, so basically utilises the post-processing, utilises point cloud data, if anybody's familiar with 3D laser scanning above water of structures and buildings, where the information is captured in point cloud. This is basically the same thing underwater. From this you can take measurements in both directions, then you can create your AutoCAD drawings in whatever plane you want, and measure out whatever repairs you have to conduct, pass the information on to a contractor, obviously used as well by the clients for as a baseline for future monitoring, and you can take whatever measurements you want from it. You can see the pink image underneath the pad, underneath the foundation, represents the piling arrangement. Here's an example here of a quay wall. Again, some early images basically capturing the debris, and you can see the detail that can be captured. The black circle in the middle is basically where the sonar head would have been placed on the tripod, and that is known as the nadir. Basically, so it's a shadow that's not captured, as you can imagine, the spinning face of the transducer. What normally happens is, if you're undertaking multi-beam sonar, it's basically remains stationary, so you can capture a certain amount of the wall, and it depends whether it's a sheet pile wall or a flat masonry wall, what the spacing or the frequency of your inspection or if your survey is along the wall. And it's very important as well to reference a point on the structure as well, so that the various images they capture can lock in the scans from one to the other, so that you can map it all together in the post-processing. Here's another example of the multi-beam sonar where we had detected scarring around the structure. Normally used in larger structures on deeper waters, where it's very important to try and capture good detailed information. And again, you can see the timber, the exposed timber piles, and again, measurements can be taken so that you can calculate the volume of any repairs or under structure repair works that you're carrying out in terms of grouting or underwater concreting. Okay, so basically the mechanical scanning multi-beam sonar advantages, it's a more customizable head positioned, so you can deploy it in certain situations for whatever you're trying to determine, where it's capturing plan view, looking down, say if contractors are constructing a breakwater and you want to make sure where the rock armour is being placed, and contractors use that quite frequently. It's also used offshore around wind farms, wind turbines, where they're replacing scar mattresses on rock armour that has been placed correctly and not overplaced, etc. Or, as I say, in situations where It's deployed on the channel bottom for detecting undermining. The disadvantage, obviously, with the 3D is that post-processing can be quite extensive. So a good rule of thumb is normally if it's 1 day in the field, it's about 3 to 4 times post-processing time required in the office. And it's obviously very important that it's undertaken by a trained technician or engineer in terms of the post-processing data, because he has to interpret the data. But it should be worth pointing out that the engineers in the field can determine for the bridge owner or the infrastructure owner if there's a problem with the structure. They don't have to necessarily wait on the post-processing data. They can be told instantly if there's an issue. So basically, in conclusion, technology is there to assist the engineer divers. It's not there to replace them, because in a lot of instances you need the engineer divers to go down and verify what's there or focus in on what's there. But in certain situations it is a much safer method of inspections, and can be used where you've got fast currents, deep waters, where you'd have to involve maybe a lot of expense if you needed a 5 or 6 person dive team with recompression chambers, that type of thing. So it certainly has its uses, and it's becoming more and more prevalent, certainly in the last 10 to 15 years. And say we've used it on a number of structures in Ireland and the UK, both in around harbours, ports and harbours, and inland waterways. Okay, just finishing off, just leaving a photograph here. Some people may have seen it before. It's actually a photograph of Malahide Bridge 24 hours before it collapsed. Just something that, you know, if you're going out conducting underwater inspections, you should always try to see if there's anything unusual taking place. So basically that turbulence, the pier at the bottom of the screen is the pier that effectively collapsed, taking down the structure a few minutes after the Belfast-Dublin train passed on the 21st of August 2009. But effectively the currents in around there, so if you look at the top of the screen, the calm waters, so obviously there's an issue there. That's why it's very important that people that are conducting these inspections are trained to conduct these inspections and determine if there's an issue. Okay, that concludes my presentation, and I'd be very happy to answer any questions that you may have.
Thanks, Brian. Fergal Cal from the NRA. You just mentioned a lot about rock armour, and like, is there any good specification for rock armour out there? Because a lot of the time when I come across it, it is really just dumped off the back of a truck. Isn't placed, it's just dumped in place. And it's very hard to come across. Well, I haven't come across a good spec where it gives you, how to place it, grading, type of rock, how you do it. So I'm just wondering, like, do you have a specification that you go by yourselves, or?
Normally you design the rock armour, like the hydraulic studies. Like the good guide would be the Syria C551 Syria guide for manual. I think it's a manual for scar at bridges and other hydraulic structures. There's good reference information in there, but effectively if we were specifying rock armour, you'd normally design it. First of all, you'd have to take account of the hydraulics. So what size of rock armour do you need to resist the flow? So that's the main issue that you design. But yes, you're right, it should be well graded material that it interlocks, because you don't want open voids in it. So you normally would specify a middle size of the rock armour and then have a certain percentage above and below that size, and again it should be interlocked so that it can resist the flow and the forces of the flow. But normally you would try to design, particularly where you've got fast flowing rivers, like say the River Shannon or whatever, situations like that, you'd certainly be designing the rock armour itself rather than just specifying it.
Great, thanks a lot.
Okay. So I've answered all your questions, and it's good.
Sorry, just pass it.
you do some calculations of scour using the ASH2 code, you often get values of 4 and 5 meters scour. Is that what you find during the inspections?
Probably not. The likes of BD 97 and other codes, we tend to find that they are conservative to a certain extent. You know, you're taking account of various factors. So it's there. We treat it as a rough guide, to be honest. So you don't rely 100% on the information that tells you, but it's certainly, we'd use it more to prioritise structures where you need to do something. A lot of the recommendations that we would make would be based on what you find in the field, as opposed to the number crunching. Because if the number crunching does show you one thing, and that it hasn't been experienced yet in the field, then you know you can just conduct monitoring of the structure. You know, immediately following a flood event, go out and inspect it. You know, it's one of those maybe high risk structures, as opposed to doing something about it based purely on numbers. You know, so I think it's a combination of both. But you usually find any major scarring occur, have to be extreme situations, or in certain circumstances something that has brought it on, like a man-made event, or severe debris or whatever gathering at the structure, you know.
Hi, Brian. Just in some, quite a number of bridges we've inspected where we found clients have installed scour protection aprons underneath them, and in a lot of cases we find they've been undermined very, very severely because either they weren't long enough upstream and particularly on downstream where they've created eddy currents and severe and it's eaten back underneath the bridge, and clients end up very disappointed that the investment they've made hasn't been while over the longer term. Do you observe much of that?
Yes, from time to time we come across that. Usually if we are specifying aprons, you try to get it towed in down below the channel bottom, so you try to determine this theoretical scar depth below the channel bottom, so at least get your toe of your apron at upstream and downstream ends towed down in below that, so that if there is currents or whatever, it'll not undermine, so give it that added protection. Usually if we're coming across a structure and we find that there's aprons added, that tells you that there has historically probably been scar issues at the structure as well. Other situations we've seen aprons being taken out because of maybe during a major flood event, one span has got trapped with debris which is forcing the water over to the other span, and obviously that extra force hasn't been allowed for in the design, and you know, suppose how far do you take it to a certain extent, yeah. So yeah, from time to time you come across that.